At Smokeless Chimney, measuring ultrafine particles is what we do. I want to explain this instrument to you. This is called a dark box. It has a 1 meter long transmissometer in it. I can flow particles through some fans. So it goes through the box. It spends about 20 seconds in the box and then is ejected out through a fan on the top. So this 1 meter transmissometer is about the most sensitive piece of equipment for measuring particles in the air that I have found. I did put this together. I did have a grant with the U.S. Department of Energy to measure smoke in chimneys, and this is a larger version of that device. I put in 2 more images of the dark box with the optical bench installed. This is a photo of the 3 candle wicks burning. It's a wax paraffin material. It's not smoldering, it's flaming, and it puts off really small particles. I'll go into that in a little bit, but this is the particles come off the flame and they go down that little fan there. And then they go through the box and they're measured and they go out the box, about 20 seconds in the box. So particles coming off of burning candles are rather small. With normal steady burning between 10 and 100 nanometers. If our beam of light has a peak wavelength of 500 nanometers, we're not going to be blocking a lot of that light. A lot of it's going to be scattered off. The blue is probably going to be scattered off, and some other wavelengths are going to be scattered off. When the candle goes out, you get larger particles. So you blow the candle out, you see that visible smoke that comes. Those are larger particles, but when the candle is burning, they're really fine particles that are going through the box. And let me show you what some of that data looks like. All right, the data from this candle run with 3 candle wicks burning, we did it 3 times for some statistical verification. We got a wavelength shift of about 2 readings with 4.4 and 1 with 2.6. That means that when the particles are in there, we get a light shift in our color of approximately 2 to 5 nanometers during the time that the particles are in the optical beam. The other readings for the candle for percent transmission is just a slight decline in, if that's in the mud of 99 or 98. So that's not you can't see this smoke. It doesn't absorb a lot of light. Kurtosis was well within the range it needs to be for. 3 would be normal. 4 is not unusual. That's all that we've got. We mainly have visuals on the particles through wavelength shift for a candle burning. That's a candle flame burning, which you really can't see particles coming off a candle very often. So here is some more data on the 3 candle wicks burning. This is test 1. You can see in the chart there that you start to see a little bit of particles in the light beam, and then this is where it's blown out. So we put progressive 1 wick burning, then 2 wicks burning, then 3 wicks burning, and then we blow it out, and that's where you get this peak of smoke here. And when we look at the color shift, we get a bit more information. You see, again, 1 wick, 2 wicks, 3 wicks, then put it out. When the smoke goes through, you get a huge color shift here, almost 10 nanometers. But you're still getting a color shift here when the fine particles are going through it. Kurtosis, again, comes in when we blow the candle out and you get the larger soot particles going through. Here's a few images of the incense burning. You can see a little bit of smoke coming out of the fan. So the incense burning, it goes into that fan, it comes out this fan, and you can see just a little wisp of it in the laser. All right, let's talk about incense burning. Incense burning puts off very fine particles. In our testing here, we have significant absorption through percent light transmission. We have 91, 84, and 87, which is noticeable attenuation of the light hitting the sensor. But we have color shift in the 12 range. See, we got 12.6, 12.9, and 12.7. That's consistent. It's really consistent light shift or color shift, and it's measurable, consistent, and when it's that consistent, it's present. It's not a mystery, or it's not a fluke. Kurtosis, again, close to 3, nothing unusual there. So this is the ultrasonic fog. So I've got the ultrasonic emitters taking the water. It's going through the fan. I got a laser that can just barely see the wisp. That's pretty thick fog in the water. It's pretty thick fog going through the fan. You can actually see it in the light when a light's hitting it. However, the laser kind of picks it up the best. What I'm trying to show here is the water makes it all the way through the box and comes out the fan. And that's when it seems we bring the box up to 100% humidity, and that's when the water makes it all the way through the box and doesn't get evaporated inside the box. So the water actually does make a pretty large particle, and the particles are persistent throughout the box and therefore attenuate the beam the most. Ultrasonic water. So we did 3 tests of ultrasonic water, and I'm not, I did a better job of capturing the light, the effluent, the fog coming off the ultrasonic water. The first test, I don't think I captured it that well. That's why we got this 91. We got 2 and 2 on the second and third. I'll do an additional test. I've got my procedure in better shape. I can reproduce that too. We've also got significant color shift. 487, 522, 528. That's significant color shift. When you're starting out with a peak wavelength of 500 and you're getting a 487 color shift, that is significant. Our kurtosis is up a little bit. We've got 8. Normal would be 3, and we've got an 8, 9, and a 17. And kurtosis of wavelength, it would normally be 300. We've got some really high readings there, so we've got some kurtosis in the ultrasonic water fog. So water fog was an interesting one. I think I can definitely get more consistent readings with further testing. Just a few images of making the 1 meter long optical bench I call the longbow or the long box, and be sure to check out our website, smokelesschimney.com.